Well, in this section, we are going to find out the derivation to find out electric field at a point on the axial line of an electric dipole. For that, let us first consider an electric dipole separated by some distance to A, where for an electric dipole we have a negative charge and a positive charge, both equal in magnitude. Let O be the center of the dipole, and from the center, let the charge be separated by a distance A. So on either side, the distance is A, hence total distance is 2A. Now, this dotted imaginary line acts as the axial line which is passing through both the electric charges. So this is the axial line where we are now going to consider a point M which is at a distance R from the center O. And we are supposed to find what is the electric field intensity at point M. So the electric field intensity at that point due to the charge plus Q or due to the positive charge can be found using the formula E is equal to 1 upon 4 pi epsilon naught Q by R squared. The distance of that point from the positive charge is found out to be R minus A. Hence, electric field due to the positive charge is 1 upon 4 pi epsilon naught Q upon R minus A the whole square. And the electric field at this point will be pointing outwards because electric field due to positive charges are always moving outwards. Hence, electric field at this point is moving out and is along the direction of dipole moment. As we know, dipole moment is always from the negative charge to the positive charge. Hence, both of them are in the same direction. So I am writing this as vector P or unit vector, which is away from the positive charge. Now electric field intensity at that point, I'm sorry it has been written as P, you'll have to please correct, due to the negative charge Q is distance R plus A, and electric field due to the negative charge which is moving inwards. So electric field due to the negative charge is 1 upon 4 pi epsilon naught Q upon R plus A the whole square. Here we find out the distances are opposite in direction. Sorry, the electric field and dipole moment are opposite in direction. So I get this as a negative vector, hence, which is towards minus Q or towards a negative charge. And since both these electric fields are moving away from each other, we'll apply principle of superposition to find resultant electric field, where resultant electric field at that point E is E positive plus E negative, or electric field due to the positive charge, electric field due to the positive charge, and electric field due to the negative charge. So resultant electric intensity at P can now be written as electric field due to the positive charge is given as 1 upon 4 pi epsilon naught Q upon R minus A the whole square into vector P. I am substituting that value over here, plus electric field due to the negative charge, which is given as 1 upon 4 pi epsilon naught Q upon R plus A the whole square into negative vector P. I'll substitute that value into this relation and now simplify this relation. I have 1 upon 4 pi epsilon naught Q upon R minus A the whole square into vector P, and this vector that we have over here, I'm using this negative sign over here, substitute this negative sign and then substitute remaining values. Find out what is common. We have Q upon 4 pi epsilon naught, which is common, so I'm left out with 1 upon R minus A the whole square minus 1 upon R plus A the whole square into vector P, which is also common. Hence, Q upon 4 pi epsilon naught into, I've taken the LCM and cross multiply to get my answers, where I get R plus A the whole square minus R minus A the whole square upon R minus A the whole square into R plus A the whole square into vector P. Continuing further, I'm going to simplify this bracket now, where to solve r plus a the whole squared, I'm making use of a plus b the whole squared, which is a squared plus b squared plus 2ab. I'm going to substitute or going to break up this bracket using the same formula into this relation. So I now get r squared plus a squared plus 2ra minus, using the formula, a minus b the whole squared is equal to a squared plus b squared minus 2ab. Substitute the same or use the same for this expression or this formula and substitute over here. I should get r squared plus a squared minus 2ra upon, we know a squared minus b squared is equal to a plus b into a minus b. This is also the same form, a minus b into a plus b, which results into r squared minus a squared the whole square into vector p. Hence electric field is q upon 4 pi epsilon naught r squared plus a squared plus 2ra minus r squared minus a squared plus 2ra upon r squared minus a squared the whole square into vector p. Strike out which are opposite, r squared and minus r squared can get cancelled. Similarly, a squared and minus a squared can get cancelled. So I'm left with electric field is equal to q upon 4 pi epsilon naught to the bracket 2ra plus 2ra, which gives me 4ra upon r squared minus a squared the whole squared into vector p. Continuing further, we have 1 upon 4 pi epsilon naught into 4ra can be written as 2r into 2aq. I have taken 4r, I have written it as 2r into 2a into q as one term over here. Similarly, the denominator again as it is into vector p, where dipole moment p is equal to 2aq. Therefore, 2aq can now be replaced by 1 upon 4 pi epsilon naught 2r into p upon r squared minus a squared the whole squared into vector p. So this is your expression to find electric field intensity along the axis due to an electric dipole. Further, if I consider a short dipole, for a short dipole we know r is much greater than a. It means the distance from the center to that point is much greater than the length of the dipole from the center. Therefore, electric field is equal to 1 upon 4 pi epsilon naught to r into p upon r squared minus a squared the whole square into vector p, which was the end result that we found using the same relation. As r is much greater than a, r squared minus a squared the whole square will now be equal to r squared the whole square. As r is much greater than a is neglected, or you can consider a to be a negligible term. Hence, r raised to 4 can be directly substituted into this relation, yielding your result to be equal to 1 upon 4 pi epsilon naught to r p upon r raised to 4 into vector p, or you can write it as 1 upon 4 pi epsilon naught 2p upon r cube into vector p, which happens to be your expression for electric field intensity at a point along the axis due to a short dipole.